Look at the computer mouse on your desk. It is smooth, curved, and fits perfectly in your hand. But before it was manufactured from hard physical plastic, how did it actually take shape? Long before a factory machine melted that plastic into a mold, this exact shape existed as pure mathematics. To get from a human idea to a physical product, we rely on a process called geometric modeling. Think of it as a translation step that turns the shape you imagine into a language that computers and machines can actually read. This diagram shows exactly where that translation happens. You can see geometric modeling sitting right in the center, the critical bridge connecting human ideas, design analysis, and physical production. Without that mathematical bridge, creating the complex, curved objects we use every day would be impossible to manufacture. Imagine a digital sculptor. But instead of working with wet clay and metal spatulas, this sculptor shapes their creations using strict mathematical rules. Working inside the computer, they build up models from the simplest possible pieces, starting with floating points, connecting straight lines, and sweeping curves. By carefully combining these basic elements, the sculptor crafts a flawless digital twin of an object, fully formed in the computer before a single physical part is ever made. Constructing that digital twin happens in stages. The first step is often building a skeleton, which engineers call a wireframe model. This is done by placing points in 3D space and connecting them with lines. This diagram shows the wireframe on the left, a hollow cage of sticks. Because the computer only sees floating sticks, the model is completely empty. Next is the surface model. The computer stretches a digital fabric over the wireframe, giving the object an outer boundary. It looks solid on the screen, but it is actually hollow, like an eggshell. Because it lacks internal mass, engineers still cannot test how much the object weighs or how strong it is. Here we see the final stage, the solid model or volume model. This version finally fills the inside of the shape, giving the digital object real mass and flesh. One way to build these solid shapes is a method called constructive solid geometry. You can think of it like playing with digital Lego blocks. Designers carve out complex shapes by stacking basic 3D blocks together, or by subtracting a cylinder out of a cube to instantly drill a perfect hole. Because the shape now has true volume and mass throughout, it acts like a complete digital twin that can be tested against the laws of real-world physics. But objects need to be adjustable. If a designer needs to change the width of a part later on, a poorly built mathematical model might just pull a part into random disconnected lines. To prevent that, we apply constraints. Constraints are specific mathematical rules locked into the model to keep its structure intact, no matter how much the design changes. This table shows these rules. The middle row uses a concentric constraint, forcing two circles to share the same center. The bottom row uses a constant angle constraint, locking an angle in place even if the attached lines are stretched. Look at the equal row on this second chart. We can take two separate uneven lines and mathematically force them to always maintain the exact same length. By locking these rules in place, constraints turn a rigid drawing into a smart, flexible system that automatically adjusts itself to new engineering demands. So what exactly can engineers achieve once they possess a fully constrained solid digital twin? For one, the computer can instantly calculate the exact weight and center of gravity for a part. It can also check how hundreds of pieces in an engine fit together, ensuring nothing bumps or interferes before a single piece of metal is cut. They can also simulate intense physical stress. By applying digital weight to a model, engineers can see exactly where an airplane wing or a mechanical bracket might bend or snap under pressure, with the most dangerous stress points lighting up in red. When the design is finalized, the solid model automatically generates the precise numerical instructions needed to guide factory robots and automated manufacturing machines. By perfectly predicting reality in a digital sandbox, geometric modeling eliminates the need to build expensive, dangerous physical prototypes just to see if they fail. Today, the power of geometric modeling extends far beyond metal, plastic, and traditional factory floors. Engineers are now taking data from medical CT scans to generate incredibly complex geometric models of actual human bone structures, like this knee joint. Doctors use these highly accurate biomedical models to practice delicate surgical operations on a screen and to design custom medical implants that perfectly match a specific patient's anatomy. Geometric modeling is the foundational mathematical language of modern creation. It provides the exact tools we need to translate the limitless ideas of human imagination into the tangible, functioning reality of our world.